As we move on to the next topic for the notes of section 1-1, we're going to be solving equations and inequalities. And there are a couple of questions that you want to ask yourself as you're solving these. First is, what is happening to the variable? In algebra, you are able to solve for the value of something that is unknown, called the variable, and in the questions we're looking at, it's going to be the variable x. X represent a number, or possibly more than one number, that will satisfy the equation or the inequality. When you look at what is happening to the variable, you need to consider the basic operations and then figure out from the second question what is the opposite operation. Operations that undo each other are going to be used in order to help us solve and find the value of the variable. The third question is, what is making inequalities different? An inequality doesn't just have one solution, it has an entire number set of solutions, but the process of finding what is happening to the variable and the opposite operation will be the same in an inequality. A couple of things to note about solving equations and inequalities. You can always check your solution. When you take your answer and replace the variable in the original equation or inequality, you can verify that your answer is correct. Some examples of some opposite operations I have listed are multiplication and division. Those are opposites. They will undo or cancel each other out. Subtraction and addition. Those are also opposites. Exponents, the opposite of those is a root. We're going to be exploring exponents and their opposite of roots in later chapters. We won't have to perform these operations in our first chapter here. Something that makes inequalities different is because you must remember to change the direction of the greater than or the less than symbol if you ever multiply or divide by a negative number. Going back to our examples, we'll pick up at example 10. We have the equation, an equal sign, and we have x plus 2 equals 5. In algebra, we want to solve to find what is the value of x. This one may seem very simple because you know the number that when you add 2 that equals 5. We want to be sure to show our work, and it is good practice to show it even on simple one-step equations like we have today. We can draw a line through the equal sign. This creates two sides to the equation. In an equation, this side must always equal this side. Anything that you perform an operation on one side must be performed on the other in order to keep the equation balanced. So right here we have x and it is being added to 2 to equal 5. Since we know what is happening to the variable, add 2, we want to perform the opposite operation, which is subtraction. We'll write down subtract 2 on both sides in order to keep the equation balanced. Adding 2 and subtracting 2 actually becomes a 0. And we still have the variable x. X plus 0 will be equal to, and 5 subtract 2 will be 3. Of course, x plus nothing, or 0, has to equal 3 means that x would equal 3. I'm sure you were able to figure that out simply by looking at the problem and realizing that, and this is how we check our answer, 3 plus 2 is what equals 5. So we knew the solution would have to be 3. We have the same problem over here, but with a little bit different symbol. This is no longer an equation, it's an inequality. This is read as x plus 2 is greater than or equal to 5. This means that there are more than one possibilities for the value of x. We're going to solve in a similar way. Draw your line through the inequality. Realize that the operation happening is an addition, so we'll subtract 2 off of both sides again to keep it equal. And we will get x and 3. We'll keep the direction of the symbol because we haven't multiplied or divided by a negative number. All we did was subtract both sides. And then we get our solution is x is greater than or equal to 3. We have a number line here to show the whole solution set, since not just one number is going to make this true. In any inequality, there's going to be a set of numbers. We show that set of numbers on the number line below. I expect my students to make the number lines contain 5 numbers. It is easiest to put your solution number here at the center, 3, and then fill in the rest of the number line. The number 1 less than 3 is 2, the number 1 less than that is a 1. Going higher, we would get 4 and then 5. To show the solution set, we will want to draw a circle at 3, and in this case, since this inequality was underlined, we will want to fill in the circle. That means 3 is one of our solutions. We can check it by putting it in here. 3 plus 2 is greater than or equal to 5. Since 3 plus 2 is 5, and 5 is greater than or equal to 5, then yes, 3 is a possible solution because it is equal. Now we need to know that x could also be greater than 3. The numbers that are greater than 3 are on the right side of the number line, and in order to show this, we'll draw an arrow along the number line showing that all of the numbers that are greater than 3 will also make this a true statement. You can check one of those quickly. Well, let's choose something like 4.5. 4.5 comes right here between 4 and 5. If I take 4.5 and I put it in for x in the original equation, 4.5 plus 2 would be 6.5. 6.5 is definitely greater than 5, so therefore this is another true solution. Again, there are going to be an infinite number of solutions. It doesn't just stop here at the number line, it keeps on going. All the numbers that are greater than 3 will work, and 3 works as well, since it can be equal to. The numbers here on the left-hand side of the number line will not work. You can quickly check one of those to verify that. If I choose the number 2, which is not in the solution set, and I put 2 plus 2, which is 4, then the statement would read 4 is greater than or equal to 5. That is not true, therefore 2 is not colored in as one of the solutions. Let's move on to the next one. We need to solve example 11 where it says x subtract 3 equals 7. Well, many of you can do this one in your head, but again we want the practice of showing our work. Draw a line through the equal sign. Realize that x and 3 are being subtracted, so we need to use the opposite operation, which is to add 3 on both sides. This will cancel. Subtracting 3 and adding 3 gets you back to where you started. So if I have a number x, I subtract 3, but then I add 3, I'll just get left with x again. Equals 7 plus 3 is 10. And we have finished. We can check your solution. Putting in 10 right here as the value of x, 10 subtract 3 equals 7. We know we have that correct. Next we have another inequality. This time we have 2x is less than 46. This time it is not underlined, so 2 times some number has to be less than 46. The operation that is connecting the 2 and the x, when there's no symbol, it is a multiplication. The opposite operation of multiplication is division. Use the division bar to show, we need to draw a line through the inequality. Divide both sides by 2. 2 divided by 2 is 1. 1x, or just an x all alone. Keep the symbol, because we did not divide by a -2, just a positive, and 46 divided by 2 is 23. 1x, or just x, needs to be less than 23. As we draw the 5 numbers on our number line, again put 23 in the center, one higher is 24 and 25, lower 22, 21, and we could continue to extend the number line forever in each direction. But we are most concerned with right here. This time our solution was at 23. We'll put a circle, but we will not fill it in. If we were to check the number 23 in our original, 2 times 23 is equal to 46, and that would give 46 is less than 46. That's not true. 46 is equal to 46, so 23 cannot be one of our solutions. We know that x needs to be less than 23. The numbers that are less than 23 are on the left side of the number line. So we will shade over here and form the arrow for the entire solution set. We can check numbers that are less than 23 to verify that they are going to make this true. Let's say we pick the number 20. 20 is down here on the number line, but it is still where the arrow is pointing. If you do 2 times 20, you get 40, and 40 is less than 46, which is true. Anything all the way up to 22 point and then a 9, or even closer to 23, would make it true. 2 times 22.9, which is very close to 23, would be 45.8. And 45.8 is less than 46. Numbers that are above, such as 25, 2 times 25 is 50, and 50 is not less than 46. 50 is greater. Therefore, 25 is not part of the solution set. Moving on to the last section of notes for the one-step equations and inequalities. In this problem, we have x over 9 equals 4. This bar right here indicates the operation of division. The opposite operation, draw your line through the middle, is to multiply. We will be multiplying, and I like to use a multiplication dot rather than a cross like an X, because it looks too similar to an X. So multiplication should be shown using a dot. The number x is being divided by 9 to give you 4. Again, sometimes people can just do these in their head, but show your work to get the practice. The opposite of dividing by 9 is to multiply by 9 on both sides. When you have a 9, that's like a 9 over 1 times by x over 9. That would be, we can also now cross simplify. 9 divided by 9 is actually 1, and then we have 1 over 1, which is still 1, and x, which is equal to 4 times 9, which is 36. Since this is algebra, you can check your solution. Go back to the original problem. 36 divided by 9 is 4. We know that 36 is correct. Example 14. This one says negative x equals 7. One thing that we know, when you have this right here, this negative sign, in front of an x actually indicates that there is something else going on. This may sometimes look like a subtraction symbol, but when it is immediately to the left of this, it can actually indicate that there is an invisible coefficient in front of the x, and that invisible coefficient is a 1. We actually have -1 times by x is equal to 7. Well, since -1 and x are being connected by multiplication, we'll want to do the opposite operation, which is division. Divide both sides by -1. -1 divided by -1 is just +1. That +1 we don't have to write as a coefficient in front of the x, and 7 divided by -1 is -7. We can check our solution by taking our answer and placing it back in the original equation. -1 times something had to equal 7. -1 times a -7, the two negatives create a positive, and 1 times 7 is 7. We know our answer is correct. Example 15. -4 plus x would need to equal -8. Draw the line through the equation equal sign and keep the two sides balanced. The x and the -4 are being added together. We want to do the opposite operation, which is to subtract a -4. Now, right here, subtracting a negative, something we should remember is that when you try to subtract a negative, you can actually add the opposite, which would be the same as adding a +4. If you have x and you're adding a -4, you could also either subtract the -4, but that is the same as adding a +4. So I will add +4 to both sides. This will cancel and become 0. X will then equal -8 plus 4 is -4. The number gets closer to 0. We can check our solution again by taking -4 and replacing it for the x in the original. -4 plus -4 would equal -8. Negative plus another negative, the answer will remain negative. Example 16. We have x subtract -4 equals 26. This is just similar to the problem before, where we realized that subtracting a negative is the same as adding a positive. I could rewrite this as x plus 4 equals 26. And then my operation is addition, so I'll actually subtract 4 off of both sides, and I'm left with just the x. These two will cancel each other out. 26 subtract 4 is 22. Checking our solution. 22 subtract a -4 equals 26. It is interesting because if you have a positive and you're trying to subtract a negative, you don't have any negatives really to subtract, and therefore you actually have to reverse it and do the opposite, which is addition. We could have also seen this if we had tried to do if we left it as x subtract a -4 equals 26, the operation of adding a -4 to both sides would have produced the same result. Subtracting -4 and adding -4 cancel, leaving just x, and 26 plus the -4 again makes it a smaller number and achieves the result of 22. Our final example, 17, has x over negative 3 being less than 13. We see the number line below, since again, not just one answer would make this statement true. We need to find all the solutions that are possible. This bar means division, so the opposite operation is to multiply. Multiplying both sides by negative 3. I'm going to put parentheses around this to show that these are connected by multiplication and that this is a negative integer. Multiplying by negative 3 and then dividing by negative 3 gives you just 1. Something that is divided by itself is always 1. X will then be all alone on the left-hand side of the bar. 13 multiplied by negative 3, a positive and a negative make a negative number, negative 39. Now, since we multiplied both sides by a negative number, and this is an inequality, we must switch the direction of the symbol. Instead of being a less than sign, we switch it to become a greater than sign. Our solutions mean that x needs to be greater than negative 39. We'll go ahead and draw these on our number line. 5 numbers, negative 39 being in the center. Going one higher than negative 39 to the right actually gets you closer to 0, which is negative 38. And negative 37. Moving to the left on a number line indicates a smaller number, and these smaller numbers appear to get larger, negative 40, negative 41, as they move further away from 0, which would be well over here. Now, the symbol is a greater than when it is not underlined, so we'll put a circle at negative 39, but don't fill it in, because negative 39 is not a solution. It cannot just be equal to. We need the numbers greater than negative 39, and the numbers that are greater are actually on the right-hand side as we go up towards 0 and the positive numbers. So, draw your arrow, including all of these as the solutions. Now, a trick that many students already know is if your variable's on the left, and that's key, if your variable is on the left, the symbol actually seems to make pointing the same point as the arrow for which way your solutions will face. This again only works if your variable is on the left. In problems where the variable is on the right-hand side, then that trick will not work. It will actually point the opposite direction. Again, we can check our solutions. Picking a number that is greater than negative 39 should give us the should make the inequality true. Let's take, for example, the number negative 30. If this is negative 37, we'd have negative 36, negative 35, etc. on the way up to negative 30. If I put in negative 30 for x, negative 30 divided by negative 3, two negatives divided make a positive, and 30 divided by 3 gives me 10. Positive 10 would be the result here. Is positive 10 less than 13? Yes. So we know that this is the correct way for where these solutions should point. If we tried something, say, down on this side, say negative 42 right here. Negative 42 divided by negative 3, well, a negative divided by a negative again is a positive, and 42 divided by 3 is 14. We'd get 14 is less than 13. That's not a true statement. Therefore, we know that negative 42 is incorrect. and does not lie in the solution set. Therefore, that part of the number line is left blank.